Hi everyone, welcome back to CS128 Honors. I'm Chen Hao. Today we're going to talk about lecture 12, which is an introduction to threads. So, starting from today's lecture and for all the way to the end of all the lectures, maybe 3-4 lectures down, we'll be talking about a really important topic, which is multi-threading in Rust. And it's one of the, I think, coolest concepts in Rust, and it's also one of the big reasons why Rust is so fun to use, especially in building complex programs. So today we'll cover some operating systems concepts, processes and threads to give a background, and we'll talk about how to actually use threads in Rust. So for those who like to follow along in the Rust book, this will be chapter 16.1, using threads to run code simultaneously. So I mentioned operating systems. So what are operating systems, right? So common OSs will be like your Windows, Mac OS, or Linux. For example, a lot of people who buy a normal like IBM laptop or Lenovo will run Windows, whereas like some people who buy the Apple ones will run Mac, right? And what does the OS actually do? So what happens is that the OS helps to manage the resources inside your computer, right? For example, if multiple programs want to run computation, they have to share the CPU time, they have to share access to the RAM, they have to share access to the disk, and so the operating system is in charge of managing these resources, right? So why do we talk about operating systems? Because they provide certain this really important thing called processes and threads. So what are processes? Processes is an abstraction of one running program, right? So for example, your Firefox program that you are running as a browser, that's one process. Discord that you're running, that's also one process, right? So when you write the Rust program and then you compile it into an executable, when you run the executable, there's also one process. So then we come to the topic of what are threads. So when in the operating system space, whenever we talk about threads, we're talking about multiple threads within one program, right? So for example, here I give an example of Discord. Your Discord is one program, but inside Discord you can have multiple threads. So maybe you have one thread in Discord that actually is listening to new messages. There's another thread to actually draw all the different UI components. There's another thread to kind of track your keyboard presses and know what messages you have typed on the screen, right? So the big idea is that each process is actually one individual program, and within each program you can have multiple threads. Sorry, my slides are stuck again. Okay, so moving on, talking about OSs and processors and threads, right? So why I mentioned the OS, because remember just now we talked about how the OS is in charge of resource management. Well, the OS is also responsible for scheduling the processors and threads, meaning the OS can decide right now at this point which process or which program has access to the CPU and which process can run, right? And the OS will switch between these different processors to ensure fairness, right? So actually, when we create multiple threads within a process, the OS is also in charge of deciding the order in which the different threads will run, right? So if we don't do any synchronization or like basically anything special on our end, the OS will actually get to decide the threads, the order in which the threads are run, and we call this like the scheduling, and basically the OS is in charge of the scheduling. So this whole concept will make a bit more sense once we start looking at concrete examples. So the first thing we need to know is that writing threads correctly is really hard, right? Because when we have different threads within the same program, they share some data with each other. And because we don't know the order in which they will run, we have to be careful to make sure that the information within that data stays consistent, right? Some examples that I've given here, for example, deadlock, where thread A waits for thread B waits for thread A, and they both get stuck and they can't both of the programs cannot progress, right? Another problem with writing multi-threaded programs is that bugs are really difficult to reproduce. Again, remember that the OS is the one in charge of scheduling the threads for you, right? So there's no guaranteed way that you know how the OS will schedule the threads. So sometimes it will be fine, and sometimes it will cause a bug. And because of that, like there is no deterministic way to reproduce the bug. We can't guarantee the exact same order of execution every single time. So I'm going to give here a small simple example of a race condition, which is like one of the bugs or like problems with concurrency programming, and it will give you an understanding of why writing threads for concurrency is difficult. And over the next few lectures, we'll talk about the kind of methods to mitigate them, as well as the structures that Rust provides you to be able to write correct concurrent programs. Right, so here we have an example. Say you have a bank account with $100, right? And you have two friends, friend A and friend B, who each wants to give you $80, right? So you expect that at the end of everything, you'll have 100 plus 80, which is $260, right? So suppose now that actually your bank account is made with a terrible bank, right? This bank has like really bad programmers, they don't know how concurrency works, right? So this is their dumb implementation of a bank. Okay, so your friend A goes to the ATM, and your friend B goes to the ATM, and they both go at the same time, okay? And the bank, we can think of the bank as like a central server, right? So now the ATM asks the central bank server, how much money does this person have in the bank right now, right? And the same thing happens on the other side, friend B who goes to the other ATM, and the ATM asks the bank server, how much does he have in his bank account now? Right, so the bank tells each ATM that your balance is $100, right? So this ATM knows that you have $100, this ATM knows that you have $100. So far, so good. Now, this first ATM, it calculates that your balance is now $180, which makes sense, right? Because you now have $100, we add 80, so he has $180. Now, the problem is the ATM now tells the server that, okay, the new balance in his bank account is $180. And so the bank server takes that as it is and replaces your old balance of 100 with 180. Now, after that, ATM B also does the same process, right? It calculates your new balance as $180. Remember, previously the bank told the ATM that your balance is 100, and so the ATM adds 80 to it. And the ATM thinks that your new balance is $180, and it tells the bank server that. So the bank server previously with $180 balance that ATM A updated now replaces it with the same amount, $180 that ATM B updated, right? So some of you might already have realized the problem, which is your final bank account balance comes out to $180 instead of $260 that we expected. But you did have two friends that both went to put $80 into the bank, right? So somehow the bank stole your $80, which is why it is a pretty terrible bank, right? So what happened in the previous slide was an example of a race condition, right? You can think of the two ATMs as two separate threads trying to share the same data, which is your bank account balance, right? And if you do not control the access properly, this kind of thing can happen where we call it a race condition because it's about who is the first to update the balance, right? Or who is the last to update the balance. And because of that, your data will be inaccurate, right? So how does Rust deal with this? We will learn this over the next few lectures. Rust uses the ownership and type system that is already inbuilt to help prevent concurrency problems, right? And if you look at a textbook, they like to call this aspect of Rust fearless concurrency. So we won't go into that this lecture. This lecture will just introduce you to how to make new threads in Rust, and then in subsequent lectures we'll talk about the techniques to deal with concurrency. So actually writing new threads in Rust is really simple. So you just import this library. So you use standard library thread, right? And then somewhere in your main function or anywhere actually, you can just write thread spawn, and then you can ignore this for now, but basically this is a parenthesis, and inside the parenthesis what happens is you give it a function, right? You give it some code that the thread that is going to be spawned will run. So the spawn thread will run the function that is defined inside here, right? So here this special function is actually called closure, and here we give a really simple example. We just have a function that loops from 1 to 10, and then it will print the number out, right? And then between each print it will go to sleep. So this thread sleep is actually a different function in the thread library that puts the thread to sleep for the duration that you specified. So here we use the duration library, and we use from millis1, which means 1 millisecond. So what happens here, right? So when you start your Rust program, there's a main function, right? So we enter here, and then now when we call thread spawn, actually you spawn a completely new thread here, and there's a main thread. So what happens here is that now you have your old main thread and you have the spawn thread, and these are two different threads now, and these two concurrent kind of lanes of execution, right? So there's no kind of way we can guarantee which one will go first and what's the order in which like the operating system will switch between one or the other thread. So we're going to see a demo right now. So this is the kind of the code I mentioned before. We import the library, and then here in the main function, I use thread spawn, where I spawn a thread that loops from 0 to 19, and it will print the number from the spawn thread, right, and sleep in between. And then here is the main, and then at the end of this spawn, here is where the spawn ends, and here is the main function. The main function will also do the same thing. It will loop from 0 to 9, and it will print, hello number, whatever, from the main thread. So let's try to run this and see what happens. So cargo build, okay, and then we run. Okay, so we see what happens here. So we see, number 0 from the main thread, then 0 from the spawn thread, 1 from the main thread, 1 from the spawn thread, right? And then it's interleaved like that. So this is kind of like a perfect interleave where it's like 0, 0, 1, 1, 2, 2, 3, 3, but this isn't always the case. So let's try it a few times. So for example, here we see that it's different. Here we have 0 from the main thread run first, followed by 0 and 1 from the spawn thread, right? And then here again we see we have 3 and 4 from the main thread before we switch to the spawn thread again. And then here we have 7 and 8 from the spawn thread before we have 8 from the main thread again. So I mean, you can notice that the order is different from the previous runs that we have. And the key point here is that the order of how we switch between different threads is not guaranteed, and it's determined by the operating system, right? So we can run it a few more times and we can see how it's like kind of different each time. Let's see. So for example here, 2 and 3 from the spawn thread runs first before the main thread, right? Here again, 3 and 4 from the spawn thread runs first, 7 and 8 from the main thread runs first. So I hope that you guys can see that the kind of indeterministic nature of all this like thread scheduling, right? So some of you might have already seen a problem here actually. So recall that in the main thread, we loop from 0 to 9, which happens here, right? The main thread loops 0, 1, all the way to 9 from the main thread. And the spawn thread, which is like we can call it a child thread, is supposed to run from 0 to 19, but it never ever reaches 19, right? So it just reaches 9 and 10, and then around then it will die and the program will end, right? So if you've been following the demo so far, you realize that the child thread never actually goes to completion and finishes its for loop. So why is that the case, right? So we notice that the spawn thread never finished, and the main reason is because the parent thread, which is the main thread, finishes before the spawn thread, right? Because the parent thread terminates, all the child thread will terminate as well. So what happens here is that you see here, the parent will loop from 0 to 9, and once the parent is done with the for loop, it will end here and it will terminate the program. Once the main thread terminates, doesn't matter how many child threads we have spawned, they will all die together with the main thread. So the solution here is quite simple. We just need to make the parent wait for the child to finish. And how does that happen? Rust provides us with this really kind of a handy construct. It's called a handle. So whenever we call thread spawn, it actually returns the join handle type, right? And you can just keep that variable. And when you're done, you can call handle.join. And what this function does is that in the main thread, when you call handle.join, it will wait for this thread that you spawn to finish. So this call is kind of a blocking call. It will wait here on this call till the child is finished before proceeding, right? If when you call this call, the child is already done, then you will just skip and go to the next instruction. So let's take a look. So it's really simple. So here we have a thread spawn, and we learned that it returns a join handle. So we can just keep get a variable to it. And then when we're done with the work of the main thread here, we can just call handle.join. And that should be enough. And so what happens here is the child thread will spawn, the parent will finish running, and then it will come here, but it will wait for the child to finish. So let's take a look. See, notice that at first the two threads are interleaving, and once the main thread the parent thread finishes its last one, number 9, the child thread gets to actually finish before the parent will terminate, right? So if we run it again, you can see that this always happens. It will basically wait for the spawn thread to finish. So lastly, we're going to talk about borrowing and ownership again in the context of multi-threading. So if we look at this example, we create a vector here, and then here we spawn a thread that actually takes in the vector, right? notice that inside the thread, what happens in the function is that it prints the vector. So Rust notices that this is a print line call, and it'll try to borrow the vector, right? But then because this is a thread that will get spawned, and it will just become a completely separate thread, Rust doesn't know whether this vector will always be a valid reference, right? So if it borrows it, it's a reference, and the reference might become invalid after some time, right? So this is an example of how it happens. So for example, we create a vector here, we spawn the thread that actually borrows the vector, and then immediately here we drop the vector. So imagine what happens if the main thread runs. So the main thread runs down here, and then it spawns the thread. But the thread that gets spawned is put on the background. It's not scheduled by the OS yet, and the main thread continues running, and it drops the vector. After the main thread drops the vector, the OS schedule the child thread to run next in the next cycle. So now the child thread runs, and it tries to print from a vector which the parent already dropped, which is now an invalid reference. So I hope that this will help you understand the problem that we have. So actually, the solution is fairly simple. What happens is that you use the move keyword when you create this thread, and what happens is that this will move the data into the thread. So this vector that we create, the ownership of the vector will be moved into this thread, and that means that here we actually can't use the vector anymore because the ownership has been moved into a different thread, and we can't use it. So, so just to recap, we talked about processes versus threads. A program is one process. Each program can have multiple threads. In Rust, you spawn threads using thread spawn. You wait for the children to finish using handle.join. And then ownership rules. Generally, we use move whenever we need to pass data into the closure. So homework 10 is released today on Prairie Learn. It's like a fairly simple example of just like the things we have gone through today on how to spawn threads. It will be due next week from now. It's next Friday, not next Saturday. Sorry for the typo. And also, we have also started to release the final project, and you can start to form your groups and think of project ideas. And the final project group's due date should be next week, and we'll update it in the announcement. So have fun coding Rust.